So good morning. I'm pleased to present you the work we did on the modeling of the geochemical and biogeochemical reactivity in underground hydrogen storage. In this work on modeling, so 3 members of the Geostock network of the CO2 GeoNet network were involved. So BRGM, Geus and CERS, and also Geostock was involved. We are interested in hydrogen reactivity because of the risks that are associated to this reactivity when we are planning a storage of hydrogen. Here I have we have a list of the different risks that can be induced by because of the hydrogen reactivity with a tentative estimation of the risk potential. First, the production of methane can induce a loss of the stored hydrogen. A production of hydrogen sulfide, H2S, can give rise to gas pollution or to corrosion of the installations. So these 3 risks are estimated with a higher risk potential. Then the production of H2S can also give rise to a degradation of well integrity. And we have also expected dissolution and precipitation of minerals because of the introduction of hydrogen that can give rise to changes in reservoir injectivity, in alteration of mechanical properties of the reservoir, or formation of a gas leakage pathway in the Cape with these 2 last risk estimating as with a low potential. And models are very useful to quantify this hydrogen reactivity. So for the given condition of storage, and that's why also we are working on the development of models. A brief overview on the hydrogen reactivity in the storage. So the expected reactivity of hydrogen during its underground storage. So hydrogen is an electron donor that can induce chemical reaction, and particular reduction reactions. And the main reactions that can be encountered in the storage are methanogenesis and sulfate reduction. So methanogenesis is the formation of methane from the carbonates, for the carbon sources we can have in the storage. So mainly if we have gas CO2 or dissolved carbonates, and potentially carbonate from rocks. And so sulfate reduction is the formation of hydrogen sulfide using the sulfate from mainly the dissolved sulfate in the formation. And an important thing that this reaction only occur when they are, or at least are only significant when they are catalyzed by microbial activity. So that when estimating, in fact, the reactivity of hydrogen in underground storage, we need to understand, to consider the activity of methanogenic and sulfate reducing bacteria and archaea, and so to consider the effect of their activity on the reactivity. And we can also have precipitation and dissolution of minerals, so mainly carbonate minerals or minerals containing sulfur. So the role of bacteria and so will depend on the condition of the storage. So there are basically two main storage. So storage in porous media, which is the earth of our interest today. So in depleted reservoir and deep aquifers, or in salt caverns. In porous media, we can have quite wide range of temperature, And also we can find a wide range of salinity. And we are expecting to have methanogens on... okay, not... okay, it's better, no? And so we can find methanogens or sulfate-reducing bacteria. In the salt cavern, we are expecting a more narrow range of temperature, but with obviously more saline conditions. So in the sump, at the bottom of the salt cavern, so we are close to the halide saturation, so with very high salinities. And so we can find halophile sulfate-reducing bacteria. And globally, we have a low knowledge on the microbial activity in these conditions. So when we are applying a high hydrogen partial pressure. So now on the models we develop and we establish to simulate hydrogen reactivity. So there are different ways to consider the aqueous redox reactions induced by hydrogen. So the reactions mainly of methanogenesis and sulfate reduction. The classical way in geochemical modeling is to consider that the aqueous reactions and the redox reactions that can occur in solution are occurring at thermodynamic equilibrium. So this is on the left. So the thermodynamics is indicating us what is the most stable species, and this most stable species will be predominant. And so with this assumption, we are expecting a complete reduction of carbonates and sulfate by hydrogen. Another way to consider hydrogen reactivities considers that this hydrogen is inert. This is an assumption perhaps valid under abiotic conditions. So without microbial catalysis, we are expecting a very low reduction of carbonate and sulfate, and that can be considered as negligible over the time scale of an underground storage. And the third way, more complex, is to consider that the microbial activity so it's governing the redox reaction, and it is implying a kinetics on these redox reactions. So there are different ways to simulate it. A classical approach is by considering the mono equation, so which is describing the reduction rate of carbonates and sulfate because of the microbial activity. And so this is an equation giving the evolution of the concentration of the different substrates of the different carbonate sulfate, depending on the microbial activity. So we can the X in the equation is the microbial concentration. So we can also have microbial growth models, and we also consider thermodynamics constraint in addition to this kinetic to the microbial kinetics. So with considering the thresholds of energy that are constraining the reactions. And just to mention that so there are high uncertainty on the rate of microbial activity under high hydrogen partial pressure. Regarding the precipitation dissolution of minerals, so we consider this precipitation and dissolution as controlled by kinetics also. So there are available databases of containing rates of dissolution of or precipitation of minerals. Here it's a list of the main minerals that can react with hydrogen. So the carbonates, minerals containing species sensitive to redox, for example, iron oxide, hydroxide. We have the case of the pyrite, of the reduction of pyrite to pyrrhotite. So reduction to iron sulfide to more reduced iron sulfide. This is well, this mostly this is a reaction that is expected to occur also under abiotic conditions. And so the sulfate or the clays containing ferric hydrons. So we use two different calculation codes, FRIC-C and CMG stars. So FRIC-C is a geochemical calculation code for gas-water-rock equilibrium and kinetic interactions under batch conditions, or in 0D or under simple 1D geometry. And CMG stars is a reservoir model which is considering 3 phases: water, gas, and oil. So it's a reservoir model in a 3D geometry that was originally dedicated to the fluid recuperation because of thermal or enhanced oil recovery processes. The interest of stars is that it includes the option of geochemical reactions, and we can also define additional reactions such as the microbial reactions. First of all, so calculation in 0D conditions, and applications to the Lobodice gas storage. So the Lobodice is in Czech Republic. It was town gas storage, so storage of manufactured gas, until its conversion to natural gas storage. And in the years before its conversion, it was observed that hydrogen was consumed, and it was and the formation of methane was noticed. So so here we have the composition of the gas at the time it was stored, and then after its seasonal storage, so 7 months later. And we see that here, for example, the content of hydrogen, we had 54%. We observe so a decrease of the hydrogen content. And simultaneously, we have an increase of the methane content, and also the carbon dioxide and carbon monoxide content were decreasing. And the interest of this storage is that it is the only storage for which we have public data. So based on we have two scientific papers describing this, giving data on that. The first approach we developed, so it's considering the assumption that we have a thermodynamic equilibrium in solution. So here in this graph we have here the composition of the gas during at its storage time, and then the withdrawal gas, so at its production. Here in the range for hydrogen, in blue for methane, and in gray for CO2. We see that with this model we have all the hydrogen which is consumed during the first time step, so leading to an exaggerated reactivity and high formation of methane. We are also predicting a very high H2S content, higher than 1%. Under abiotic conditions, so our model considering that hydrogen is inert, we observe no reactivity. So it means that without microbial catalysis, the mineral reactions alone are not able to consume hydrogen, and so this model also is not able to reproduce the gas composition evolution. So the third approach is by considering microbial kinetics of the aqueous redox reactions. the first step that we need to calibrate the kinetic parameters. So it's here it's on an experiment of hydrogen consumption by the microbial consumption samples in the low body chair reservoir. So we reproduce the formation of methane that was measured so in this experiment, so that we have kinetic parameters we can use. But in fact, using this kinetic parameter determined in a laboratory experiment, we still have a reactivity which is too fast, which is this line here. So so we have a complete consumption of methane in some days or some weeks. But the gas composition evolution can be reproduced with this model, considering some microbial kinetic. But we need to adjust the kinetic parameter, and we have to achieve the reproduction. We needed to divide our methanogenesis rate by 50. We also are predicting some production of H2S, but there is I'm not very confident in the value because we had no measurement of H2S in low body Che available. Regarding the mineralogical evolution, with the three models we have the same evolution, and globally we have no reactivity, with the main simulated reaction being a progressive dissolution of gypsum. According to the mineralogical analysis, we have less than 1% of gypsum, and some of this gypsum was dissolving. And yes, to mention that we have the carbonate minerals, so you are not seeing any variation here, but they are very active in, they are participating in the pH buffering, so they have an influence also. And so regarding the pH, we see that we have an efficient buffering by the carbonate minerals, with the pH being keeping in the same half pH unit. And we see some variations because pH tends to increase with the dissociation of hydrogen in water, and it tends to decrease with the production of H2S, so that's why we have some variations. Now the models, the 3D model, so the reservoir model, considering also hydrogen reactivity. The first step is also to obtain kinetic parameters. So here it's a modeling of a high pressure experiment for hydrogen consumption made by MicroPro. And so we were able to, we simulated this experiment to have the kinetic parameters we need, so with the reaction rates, etc., the different the half saturation parameters we need for methanogenesis and sulfate reduction. Just a brief comment on the pH, as Björn was commenting, that we have the outgassing of at the end of the experiment, and where we have we need to consider this outgassing, just to comment. Okay, so once we have these kinetic parameters, the next step, in fact, before implementing it in stars, so in the 3D models, we have the difficulty that we are not exactly the same formalism of the reaction between the mono equation and the stars formalism. So it has been necessary to feed the two parameters of the stars formalism to reproduce the kinetic rates we have, where we determine on the mono equation. So globally, we are quite close with stars. perhaps have a faster reaction rate under at low concentrations, but it converges when the concentration increases. The next step, the next difficulty, is upscaling from the lab to storage condition. In fact, it is because of the differences of volume between the experiment and the mesh we are considering in our reservoir model and in the reservoir in itself, and also because of the rock, water, and gas ratio. So in terms of volume, for example, we have 4 order of magnitude of differences between the experiment and only one mesh of our model. And we to be able to measure something on the fluid evolution, we have in a laboratory experiment, we generally have less rock than gas or water, while in a porous media we have more rock than water. Also, we have different conditions in terms of for bacteria with optimal growth conditions and more starving conditions in the real life in the reservoir. So we determine an upscaling factor to slow down the reactivity between the laboratory and storage condition, based on approximation in reservoir modeling, based on previous study of reservoir modeling. So this is a model presented before by Jan. So the conceptual reservoir model with the different injection wells, and we simulated different cycles of injection and production of hydrogen. So in this, so this is initially it is fully saturated in water. It's a deep aquifer. And we are injecting pure hydrogen, simulating different cycles for pure hydrogen. So this is after some cycles, the map of the distribution of hydrogen, methane, H2S we have in our model. So here in the left is by considering laboratory parameters, and upscale kinetic parameters on the right. And in the different columns, so we have the content of hydrogen in the gas phase, methane in the gas phase, H2S in the gas phase. Here, hydrogen, methane, and H2S dissolve. And here for gas and dissolve for methane and nitrogen. So we see that we see a plume of hydrogen gas which is developing, so in the reservoir, and we see the formation, the generation of methane or H2S at the edge of the hydrogen plume. So at the front, where in fact hydrogen meets the fresh brine because the reactions are occurring in solution. Okay, and with kinetic parameters upscaled to at the reservoir scale, so we have less reactivity, and in particular we are not seeing the apparition of the formation of H2S. The same result, so the evolution over time. So we are looking at the composition of the withdrawal gas. So here we have the different cycles. Here it's the first cycle with the injection and the production, second cycles, etc. In green, here it's the hydrogen, in blue the methane, and in the red H2S. We see an apparition of methane and H2S when we are considering the laboratory kinetic parameters. We are only seeing methane, so considering a reservoir, upscale reservoir parameters. Okay, and what we see is that the reactivity is higher during the first cycles, and then it tends to decrease. and that we are recovering more hydrogen over time and over the different injection production cycles. And also that the results are highly dependent on the upscaling factor. And so it's still a challenge to define the right parameter for reservoir model. So I'm reaching the conclusion. So as a synthesis, so we developed a reactive model in 0D, so both to simulate laboratory experiments, also they are useful for first evaluation of the hydrogen reactivity in the storage. We are also working on the development of 3D reactive transport models to consider the storage and withdrawal cycles and to predict the reactivity at the reservoir scale. And this model are, the goal of this model is to help in the evaluation of the risk due to the reactivity under hydrogen storage and the associated cost, so regarding gas treatment, loss of hydrogen. The design also can be useful. We have seen that stills, the behavior of stills in presence of hydrogen can be different depending on the H2S content, for example. In terms of perspective, we need still more calibration on the reservoir data to calibrate better the models. And to mention that we have an uncertainty on the microbial kinetics, and there is this difficulty of the lab-to-field scaling, of defining lab-to-field scaling factors. And something that could be interesting is to better consider the environmental factors on the microbial activity and to be able to consider something closer to what is occurring. You can find more details in the paper we recently published, so on the modeling approach and on the application to the Lobodice Tonga storage. There are also 2 public deliverables on the Hystories website. And so I would like to thank you.
So we have 8 minutes for questions.
So starting with some questions from the chat. Do you have evidence that the risks of alteration of mechanical properties of the reservoir and formation of gas leaks, pathways in the cap rock are low?
This is based, in fact, in our calculation. We are seeing that we are not expecting high mineral changes, and there are some papers that mention the possible alteration of the mechanical properties, but it was based on perhaps an overestimation of potential dissolution of minerals. So with very low dissolution expected, we don't think that we will modify importantly the mechanical properties.
Maybe another one from the chat. So a bit of a long question, so please bear with me. In this modeling study, I'm missing the abiotic reduction of pyrite by hydrogen, which can create H2S. That is likely not very relevant at the conditions of this study. At temperatures where microbial activity are limited, 80 to 120 C, this abiotic reaction can still generate H2S at levels relevant for consideration for materials, gas pollution, and HSE. What is your view, and how should this be modeled?
So in the application case I show you, so in the mineralogical analysis there were no pyrite, so I didn't consider pyrite to pyrrhotite. But yes, it is reported that this reaction can occur even at a relatively low temperature, perhaps at about 100 degrees, and can be significant, but can be estimated and calculated.
Patrick Egerman, Storengy. So thank you for the nice presentation. So I think you raise a key point with the upscaling topic. So we know this is a key step to bring the result from the lab to the field typically. But we know it will be complex. So we know because we have heterogeneous reservoir and so on. So it will bring its own level of uncertainty to the final results we will obtain. So from your understanding, do you think we can escape somehow to perform a pilot to calibrate the upscaling factor?
Yes, it will be very interesting. We have data from pilot and from real field experiments. Well, the goal of this presentation of the result, mainly on the 3D result, was to show that we can have very different results depending on what we are considering in terms of reactive rates. So that we have well, we have tools. We are starting to understand what is occurring, but we need to calibrate better, to adjust better. That wasn't the question.
After your presentation, it seems to me pretty clear that we will have to go for a pilot.
Yes, in porous media, it will be very interesting.
To reduce uncertainty.